Good morning, good morning, everyone. Welcome to the CME Bharat seminar series. It is a pleasure to introduce our speaker today, Dr. Saurabh Singh, Associate Professor in the Astronomy and Astrophysics Group at the Raman Research Institute, Bangalore. Dr. Singh's research focuses on probing some of the least understood epochs of cosmic history, including the cosmic dawn, the epoch of reionization, the era of dark energy domination. Using one of the promising tracers, the redshifted 21 centimeter signal from neutral hydrogen. The signal, though incredibly faint, carries a wealth of information about the early universe. Detecting it, however, is no small feat. Foregrounds from our own galaxy are nearly 100,000 times brighter, and the challenge is compounded by the need of extreme control over instrumental systematics. To meet these challenges, Dr. Singh leads efforts in designing, building, deploying custom radio telescopes tailored for this delicate measurement. His group is behind cutting edge experiments such as Ceres and Proteus, and he also collaborates with major international efforts including Hera and Chime. These projects employ different techniques but share common goal of detecting the redshifted hydrogen signal across cosmic time. Dr. Singh received his PhD in 2018 from the Joint Astronomy Program at IISc with his doctoral work conducted at RRI. He went on a postdoctoral position at McGill University, where he worked on experimental observational radio cosmology. He holds a BTech in Electronics and Communication Engineering from IIT ISM Dhanbad. Today, Dr. Singh will be speaking on Whispers of Hydrogen, a 21 centimeter window into the early universe, where he will talk through the science challenges and recent advances in uncovering the cosmic past through one of the nature's most subtle signals. Please join me in warmly welcoming Dr. Saurabh Singh. Dr. Singh, the floor is yours.
Thanks a lot, Arithro, for the beautiful introduction. Let me just try sharing my screen. Yeah, can you see the full screen presentation?
Yes. Yes.
Okay. So thanks everyone for joining today. And yeah, so as Arithro said, I would be talking about how we can use 21 centimeter signal from the neutral hydrogen to probe different times in the cosmic history. And I believe that we have not really covered 21 centimeter physics in this seminar series. So I'll spend some time in trying to motivate on why this is important and what is so unique about using 21 centimeter signal to actually do cosmology. So of course, I'm sure every presentation in this platform would start from some representation of cosmic timeline, and this is no different. So we are here at the center of the universe, and I'd mostly be talking about in terms of cosmological redshifts. So cosmological redshifts are proxies for time, which is we are probing right from the time when the cosmic microwave background was emitted all the way to the current universe. So higher the redshift, the farther in time we are looking at. So just to give a rough mapping, we expect CMB to be around 400,000 years after the Big Bang. And the current age of the universe is around 14 billion years. Now, what interests me mostly are these intervening stages. So we know that the first atoms had already formed and the photons and the matter had decoupled by the time CMB was emitted, which is around redshift of 1100. Soon after, what we expect is presence of neutral hydrogen gas mostly, and there are photons, the CMB photons, which are free streaming. But there is nothing really happening. It's kind of uneventful period, but it has its own unique motivation to study because it's a test bed for many cosmological models. So that is what we would call as dark ages. But then things will become more eventful the time when the first stars and galaxies form. And this is what we would call as cosmic dawn. So cosmic dawn is important because this is the first generation of stars and galaxies, and we quite don't fully understand the way they are formed, the time at which they are formed, and how different they are in their properties compared to the generation of stars and galaxies that we see in the local universe. Now, when these sources of radiation emerged, they did two drastic things to the IGM, the intergalactic medium. The X-rays from these sources heated up the IgM, and therefore they changed the thermal history. At the same time, there are also these UV photons which are being emitted. And these UV photons essentially start depleting the gas in the intergalactic medium. So soon after their formation, we have epoch of reionization. Reionization, because universe actually was ionized, as a matter of fact, it was plasma before CMB, it became neutral, and now it is ionizing again. We expect it to have ended around redshift of 6 based on other observations. And of course, 21 centimeter signal cosmology doesn't end here. You could also use the same signature to probe various later redshift. I'm not sure if I'll be able to get into that, depends on the time. But I would want to mostly talk about the cosmic dawn and reionization as the primary times which we want to probe using 21 centimeter. So this is a crucial epoch. So in terms of times, roughly around 100 million years or so, we expect the very first sources of radiation to form. Initially, these sources are very local, and most of the UV photons actually don't escape. So the ionized regions are all very confined. But that changes as more and more sources form and their ionized regions start to overlap, which is what you are seeing here. Now, suddenly these UV photons have a huge mean free path to travel, and they can start depleting the gas at much, much larger lengths. By roughly a billion years after the Big Bang, which is redshift of 6, you do expect almost all the gas in the intergalactic medium to have been ionized by the sources for stars in galaxies. So this is basically the full picture that we want to probe here. And the probe that we are using for this is 21 centimeter. By no means this is the only probe, right? So you must have heard outstanding results coming from JWST, for example, which is probing almost this shell, which is redshift of 10 to 15, and it is picking up these individually bright, massive star-forming galaxies. However, the problem there is you can only pick up the most massive, the most bright galaxies. But what we understand from the structure formation is most of the galaxies there are dwarf galaxies. They have smaller mass and low brightness. And that is very hard to pick up by the traditional optical telescopes or IR telescopes. And that's exactly what we would want to do. We are not interested in picking up individual galaxies, but we are basically interested in what we call as intensity mapping, where you don't look at each source, but look at overall property of the IGM. So that is precisely what we do with 21 centimeter. The advantage is, unlike optical, which gets very quickly restricted in their sensitivity, with 21 centimeter emission, you can probe much higher into redshifts or much farther in time. So you could go all the way to almost touching the dark ages using 21 centimeter hydrogen. So this is basically a spin flip transition, as you may be aware of. Other beauty of this signal is the redshifting, right? So depending on at what redshift it's emitted, it gets redshifted by the time it arrives. So a signal which was emitted from redshift of 150 will appear at a different frequency in our observer's frame compared to something that was emitted at redshift of 10. And it's a very straightforward relation. It's emitted at a restrained frequency of 1420 megahertz, and it's basically divided by this 1 plus z, right? So at the signal that is coming from redshifts of 30 would be at 46 megahertz. So in some way, the rest frame is 1420. When you design a telescope, you can design to have measurements at different frequencies. And each frequency basically corresponds to one slice on this plot, right? So in some way, you can tune this entire range of shells by a single instrument that can make a broadband measurements. So in the future slides, I'll be basically using frequencies, but the implicit assumption here is that each frequency studies a particular redshift. Now, what is it that we actually measure, right? So I say, okay, it's 21 centimeter brightness, but it actually depends upon a lot of quantities. As a matter of fact, at different redshift, it measures very different quantities. So let me just spend some time in trying to expand this. So what we measure is delta TB, which is the brightness temperature of the 21 centimeter signal. The first quantity and probably the most sensitive quantity is the Ts minus Tr term. So this is the spin temperature of your hydrogen gas, which for all practical purposes, for the kind of redshifts we are talking, is same as the gas temperature. The TR is the background radiation temperature. So in standard models, we would assume the background is basically the CMB. And what we measure is a contrast between the gas temperature at given redshift as seen in the background of the CMB. So that is this term. And this is very important because in some way, the change in brightness at different redshifts can be translated on how your gas is getting heated. At much later redshifts, so we are talking now at least redshifts of 10 to 6, there is a substantial reduction in the neutral hydrogen itself, because by this time your UV photons have started escaping the halos and getting into the intergalactic medium. And now the H1 starts to decrease, and therefore the brightness temperature will reduce. So at lower redshifts comparatively, XH1 takes over, while at higher redshifts or the farther times, you are measuring this quantity. So in some way, you are probing the thermal history, also the ionization history, using a single signal. Now, you can study a lot of things in 21 centimeter signal, and there are people who actually do all of this. So this is a light cone. This is from a simulation where you start with a very neutral gas, which is very cold. So as you know, this is TS minus TR, which is gas temperature minus the CMB temperature. So at those redshift, your gas is colder. Therefore, this term will be negative. So what you see here is blue, which is basically negative. The units are millikelvin. This is just a representation. We measure power in terms of kelvins and millikelvins, but they can be readily converted to the more conventional units. So essentially there is cold gas and therefore the signal is negative. Once the X-rays start to heat the gas, you have slightly higher signals. And at some point, your gas temperature is hotter than the CMB. And this is where you expect the signal to be positive. So these red colors. But by the time that happens, you are also looking at some very nice morphology. And this is because the black regions are basically where you don't have any neutral gas. So it's completely ionized, and therefore there is no brightness associated with those pixels. And this morphology is a very strong tracer of what kind of sources ionize the universe. So this is the overall picture that we want. Ideally, in order to understand it, we would actually want this image, right? But that is very tricky. And therefore, we want to do some statistical measurements. So the easiest thing that you would want to do is at every redshift, you can take the mean brightness, right? So basically a vertical line and a mean of that vertical line. That is what we have plotted here. So x-axis is frequency, which can be translated to either cosmological redshifts, or it can also be translated to times. Lower frequencies means farther in the cosmic history, higher frequencies closer to us, or low redshifts. So this very particular signature that you see, initially you have a negative signal because the gas is cold. Then the signal is getting towards positive because the gas is getting heated. And essentially it's dropping to zero because by this time you have substantial reduction in the neutral hydrogen fraction. So this is the mean evolution. This is what I would call as the global signal. Why global? Because there is no particular pointing. In traditional astrophysics, you would want to observe a particular source, particularly galaxy. But this is an all sky signature. It doesn't need a specific pointing, and therefore it's global in nature. But that's not the only thing. It's fairly non-Gaussian field, as you can see, unlike CMB anisotropies, which are very Gaussian. So you can look at higher order moments. The first thing is, of course, the variance estimates, which we would call in Fourier space power spectrum. So there are experiments that measure at different spacings how the power changes. So for global signal, you can actually do that with a perfectly calibrated single element telescope. And I'll come back to what I mean by all of those terms. So this is one example. This is our in-house experiment called CERES that Arithro had pointed out in his introduction. But then for power spectrum, you can't possibly do that with a single telescope. You have to use the full array or interferometer. So one example is this Hera experiment that I'll be talking about a little bit. And then also how we can combine these things together. So the hunt for this started really long ago. The earliest work that I could find is roughly in 1977 on your left here, which was talking about the signature we would expect in the dark ages. And of course, back then, we hardly had idea about our constitution of universe, about omega m or different densities. And therefore, for different variations of it, there were signatures expected. This finally came into a much mature field in the 90s and early 2000s. This is one of the first papers by Shaver and others in 1998 that questioned whether can we detect a global signal in the 21 centimeter. And I love this paper by Martin Rees in 1997 that was talking about similar things, but it, in its own unique way, focuses upon the challenge here, which is it is not necessarily unfeasible to distinguish the 21 centimeter with everything else, right? So this basically lays down on why this is such a challenging area. But why is it worth it? Is because the amount of information it withholds about the nature of our stars and galaxies. So on this plot, it's a fairly busy animation by Andre Messinger, who is a simulator in our field. And all these variables that you see are the free parameters of our problem. These are all related to the properties of the first stars in galaxies. So you have ionization efficiency, you have the minimum mass, which can be translated into temperature, about the halos that can form stars. You have some properties of the X-ray sources there, mean free path. So as they change, and of course, these are completely free parameters because we have no clue what these were for the first stars and galaxies. So for each choice of these parameters, you will see how the light cone evolves. This is a function of time and therefore frequency. And then correspondingly, how the global signal evolves and how the power spectrum evolves. Okay. So for some parameters, you can see things are very sensitive. For some parameters may not be the case. But this basically gets the message across that if there is a detection of global signal or the power spectrum or both, it will, in some way, we can reverse engineer this and constrain the properties of these first stars in galaxies. So even if we are not measuring the very top row, which is the light cone, we should be able to measure these statistical quantities and do a lot of astrophysics with such measurements. Okay. So unlike other cosmological signatures, which is what we are used to seeing probably on this platform, the 21 centimeter signal is unique because it's not deterministic. So even if we assume it's lambda CDM model, just the sheer uncertainty in the astrophysics of these first galaxies give you a range of models. So this is our collaborators at Cambridge now, who have done a lot of very nice work on trying to explore all the possibilities of what the signal can look like, both the global signal as well as the power spectrum. So you can see the global signal. This is a function of frequency, correspondingly redshift or time. And this is the brightness temperature. The typical units are millikelvins or hundreds of millikelvins. On the right side is the power spectrum, again, as a function of different redshift. But power spectrum has one more axis, which is different spatial scales. So here we are looking at a very specific spatial scale. And this is the brightness temperature. Of course, it's a variance estimation, so it's millikelvin squared. But what I would like to emphasize here is the sheer brightness, or rather the faintness of the signal when compared to everything else. So why is this so challenging to be able to detect this? And that basically encompasses everything which is there between our telescope and the signal that we are looking for, right? So on the right side is a measurement that we have done at a radio observatory close by Gauri Bidnoor field station. And on the left side is showing all the constituents that are present in this data, right? So you have, of course, have the signal of interest, but then at the same frequency range, which is roughly 40 megahertz to 200 megahertz, corresponding to the redshifts of 35 to 6, you have these extragalactic sources as well as their own Milky Way galaxy. And these radiate very strong continuum emission, what we call a synchrotron radiation. There are other also components in the measurement. Then you also have ionosphere, which is highly frequency dependent and time dependent. So it has refraction effects, absorption, as well as emission, which of course is higher than the amplitude of the signal that you're looking for. Closer to home, you have radio frequency interference, right? So these are terrestrially generated sources like FM, TV stations, etc. And finally, you have your own telescope, which is non-ideal. So what you measure is not just the signal of interest, but every possible thing that we just talked about. And that's what the data represents. So some of these components you can see directly. For example, these vertical lines are nothing but radio frequency interference. And these are probably the easiest to detect because they are very strong. And for example, this is FM. So that is 87.5 to 108 megahertz. You have a bunch of lines at very low frequencies coming from all kinds of sources. You also have a baseline shape here. It's not flat, it's power law-like, and that is coming from our own galaxy. And finally, you have somewhere deep embedded in that the signal of interest. I have a question here, I think, in the comments. What's the origin of astrophysical uncertainties? Is it our lack of understanding of the astrophysical phenomena or observational precision or something else? Great question. I would say it's a mix of everything. First of all, we probably don't understand the astrophysics itself at very high redshifts. And because the local universe astrophysics is very strongly constrained from the observations, right? So you have in a very high accuracy, you have measured the star formation efficiency, for example, or the distribution of masses in our local universe, or even their luminosities in X-ray and radio and other wavelengths. None of these have been observed at very high redshifts. So how do you extrapolate a local universe measurement to high redshift when nothing is constrained? That is the biggest question. And therefore, all the possibilities that you saw was basically, browsing over all the possible parameter spaces, which are completely unconstrained right now. Okay, so moving forward, the first thing that I mentioned was foregrounds. Honestly, it is very high, of course, but the spectral features in the foregrounds are very different from the spectral features in the 21 centimeter signal. And this is something that I'll keep coming back to. So on the right, what you see in the blue line is an expectation of what the galactic foregrounds would look like at different frequencies. This is a sky average. And the typical numbers to keep in mind is something between 10,000 Kelvin to 1000 Kelvin. On the same axis in the log scale, I have plotted the magnitude of the signal, different colors showing the different kind of signals based on the astrophysical model. And these can range anywhere between a few millikelvins to hundreds of millikelvins, right? And you can see the order of magnitude difference. But you should also appreciate that the spectral behavior or the frequency behavior of this signal is very different from the frequency behavior of the foregrounds. And therefore, if there was nothing else in the picture, it's just these two things, I think we have some idea on how to deal with the foregrounds. But this problem is completely changed or made more difficult because your instrument itself is very non-ideal, right? And I'll give you some examples on how. So our design philosophy is whatever our instrument does, it should not compromise the spectral nature of the signal or the foregrounds. Basically, the foregrounds are intrinsically smooth in frequency space, and we would want to keep it that way. So your instrument should not introduce any feature that can have lots of spectral features in your measured data, and that will make your separation between the foregrounds and the signal very difficult. But unfortunately, in our experimental setup, there are lots of things that can do precisely that. So I'll just explain two things on this. The first is your field of view itself, what we call as the primary beam of your antenna. So all our radio telescope will have a sensor, which is the antenna, and its frequency response. So how its field of view changes with frequency can be actually very different. It's very difficult to design an antenna that looks at the same region of the sky across all the frequencies. And here we are really talking about a wideband range, not a particular narrowband measurement. So why is it so important? Suppose I have a galaxy here, which is intrinsically a flat spectrum. So it has the same intensity across all the frequencies. But then my field of view is changing. So at higher frequency, my response is minimal. It is shining on what I would call a second side lobe. But at some intermediate frequency, there is no response. And at them some further lower frequency, it has a slightly enhanced response. So this galaxy, which was flat intrinsically, what I would measure would look something like this. And this is concerning because my signal also has same kind of features, as you can see from here, right? So you would not want your instrument to be introducing something like this, right? And the same thing can happen in multiplicative features of our experiment. So we have what we call as gains, right? So you have amplifier, you have filters, all of them have frequency dependent response. So for example, this is the real data from our experiment. We are measuring the brightness temperature at different frequencies. When you don't have these corrections, the multiplicative impact, both from the antenna side, also from receiver, you have something like this. And people in the field will definitely disagree that it looks anything like foregrounds, right? Because there is a frequency response which has been multiplied to it. When you undo that, you get back the blue line, which is closer to what you would expect from galactic emission. So one has to then undo most of these things in order to recover the signal of interest. And this is where the most of the challenges lie. So we would call this all of these corrections under a single umbrella calibration. So how do you calibrate your telescope to a very high accuracy? And here we are talking about accuracy of around 1 part in a million to 1 part in 100,000. How do you calibrate your telescope to that accuracy over this entire range of frequencies so that you can finally separate these foregrounds from the signal that you're looking for? So I'll now go over the two modes of observations, having kept in mind that these systematics are very important. The first set of experiments deal with power spectrum measurements. So just to recap, these are fluctuation measurements of the 21 centimeter line. And there are lots of experiments right now who are trying to detect this, right? So you have LWA in the US, MWA situated in Western Australia, HERA experiment, which is in South Africa, LOFAR in Netherlands. Of course, we all know GMRT here. And then upcoming is SKLO, which is roughly 130,000 log periodic dipole antennas. And one of its science goal is the 21 centimeter detection from the cosmic dawn and epoch of reionization. So I would focus on HERA experiment with which I work closely. And just to give you a flavor of what kind of experiments are required and what kind of challenges they have. Okay. And this is exclusively for powered spectrum. So the HERA experiment aims to, of course, detect the powered spectrum between 50 megahertz to 200 megahertz. So that would translate to redshifts from 30 all the way to the redshifts of 6. I have a question, another thing, which is, wouldn't the foreground be different as we vary the angle, but the signal is global and they should have the same features across the entire sky? Great question. That is correct. So if I look at the foreground map, the absolute brightness that you would measure will definitely change with time. Time here means pointing because your telescope usually doesn't move. So as different regions of the sky will come in your field of view, you will measure different brightness temperatures. Having said that, we expect that the spectral behavior of these, independent of where you are, will broadly be power law like. And I put it in double quotes because there will be subtle changes in the spectral nature depending on where you are looking. But the fact that they will continue to remain spectrally smooth, especially when you are looking through a very wide field of view, will be valid independent of where you are looking at. Okay. Okay, so as I said, HERA is one of such experiment. It has these antennas which are expected to be roughly 350 in number when it's completely built. It's in a mode where it's also being built, but also observing at the same time, which is a very quick feedback both for science, but also how you can improve your experiment. As I said, these are drift scan telescopes, which is they have no moving parts. So you're looking at a stripe on the sky, and as the sky moves over your antenna, you sample different regions of the sky. So this is the stripe centered at minus 30 degree declination. This is basically the latitude at which HERA is located. You will see different regions at different times. And these times actually can be covered in 24 hours, but we only take nighttime data. So this can only be covered over several months. You don't have to do your analysis over all the regions of the sky because some regions of the sky probably are more complicated to model compared to others. So you then now have a liberty of choosing different fields. And therefore you can, because as the comment, this question was, the signal doesn't change with your angle or your declination or right ascension. So you can comfortably choose your foreground regions, which are probably low amplitude, but your signal will remain there. So in some way, your problem gets a little easy, but not by much. But then the question is, how do you calibrate such a thing, right? Your system here is fairly complicated. It has all kinds of primary beam effects, a lot of multiplicative receiver calibration effects. So I don't have time to get into the details of how do you calibrate interferometers, which can be an hour-long talk in itself, but I will give you just two broad examples of how do you do that. The first example basically is the sky-based calibration. So when you're looking at a picture like this, you exactly know what region of the sky you are looking at. You can create very intricate models of all the point sources, all the diffuse emissions in that particular region as good as you can. And then you can use that to subtract all the sky from your images. And that is a technique that, for example, LOFA telescope here uses. And it has gone very deep in its sensitivity to measure all kinds of faint point sources and construct an accurate model. Of course, here the disadvantage is how complete your sky model is, right? Can you ever reach a level of completeness where you can subtract the full foreground sky? That's a question that has not been answered yet. Hera employs a slightly different strategy, what we will call foreground avoidance. And this ties up with the spectral nature of these foregrounds. So in the frequency space, the foregrounds are spectrally smooth. So if you took a Fourier transform of this, they will be contained in very narrow regions of the Fourier space, which is a common principle. If you have a broadband feature in one Fourier space, in its inverse Fourier space, it will be narrow band. So all these foregrounds in principle can be contained over a very small range of Fourier modes, what we would call as delay modes. So if you did everything right, if you calibrated your experiment right, you can go to the Fourier space and basically subtract or rather just avoid those modes which you think are contaminated by foregrounds. And therefore, you can only do the higher delay modes where you expect to be dominated by 21 centimeter signal. And the way to calibrate such a thing is what we would call a redundant calibration. So you can see these dishes are arranged in very regular grid, right? And same sky is measured by multiple combinations of these antennas. So you can in principle use this to basically calibrate your experiment. I can't go into the details. I'll be happy to take questions later, but this is called redundant calibration. You don't need a very complete picture of the sky as compared to the sky subtraction approach. But here also there are disadvantages. How do you know that the different combinations of antennas are measuring exactly the same thing? Are baselines really perfectly identical? Are the antennas perfectly identical? Probably not. So there are what we would call non-redundancies, which can in principle lead to miscalibrations. But again, none of the methods are perfect. And therefore, both these strategies, whether you subtract the foregrounds or whether you avoid the foregrounds, you will have some level of systematics in the regions where you don't expect. Okay. Having said that, Hera has been observing for a while now. Sorry, there is another question. Why do we worry about identifying the point sources since we are anyway going to average them through the entire sky? That may not be completely true for interferometers. You are very sensitive to even the point sources because your beam is fairly narrow. And then typically in interferometers, we don't average over different what we call as here equivalent of right ascensions. So what we do is we take one field and we basically analyze over that field. But before foreground subtraction, it's actually difficult to average all of this. This is something that we do in the global signal, which I'll come to. Okay, so Hera has been observing for a while, and the first season of observations were between 100 and 200 megahertz. And so this would correspond to redshifts of around 10 to 6. What you are seeing is how the total power changes over right ascension, or rather time. And based on this, you could do some kind of avoidance and only look at the Fourier modes which were non-contaminated. And that is the plot that you see on the right. I will be showing these plots very often. They would be basically power spectra, where you are looking at how the power is distributed at different angular scales on the sky. So this is in some way very similar to CMB power spectrum that you may have come across. But instead of using multipoles, we will be using K, which is inverse megaparsecs. So the black line here is what we would expect if we were only limited by thermal noise. You can't really do better than your thermal noise, but it's a good condition to be limited only by thermal noise. So if you have systematics, for example, you will have some excess power, which will never average, unless, of course, you model it. But if you're only limited by thermal noise, it's random in nature, and therefore it helps to have then more data and then average it to unlock lower and lower sensitivities, or rather higher sensitivities, lower amplitudes. So we already achieved fairly good sensitivity, roughly a few hundred millikelvin squared. It's a non-detection, so we have not yet detected the power spectrum. None of the experiments have, as a matter of fact. But this is really good to be now placing constraints on what kind of power spectra are already ruled out. So if I take you back to the different power spectra here, some of them are really high amplitude. As a matter of fact, we have measured those and not found them. So this actually helps in ruling out a set of these models and therefore in turn constraining some parameter space from the early universe. So that's what precisely we did with Hera with this powered spectra. So for example, if your X-ray sources are very bad at heating the gas, so they have a very poor efficiency, your gas is going to be very cold. A cold gas is easier to detect because your signal amplitude is high. The reason you'd never detected them means that the X-ray efficiency is basically higher, right? So you could constrain the X-ray luminosities of these very first stars and galaxies. So that itself, a non-detection, which is sensitive, can lead to a lot of nice astrophysical constraints is one of the take-home messages. Where our community is in the power spectra, that is shown on the left side. So we are looking at the fluctuating component, millikelvin squared, and at different redshifts over a different range of spatial scales. The magenta points are what we have done with Hera at these two redshifts, one around 8 and one around 10. And the blue lines, the orange lines, these are all different experiments. As a matter of fact, the very first experiment that had an upper limit was our own GMRT here. And since then, a lot of other experiments have come up. MWA paper was a predecessor, and then LOFAR particularly, to have some upper limits. But as you can see, none of them are close to the standard signals. They have been able to rule out a lot of signals, but the more standard ones, we haven't reached the sensitivity. We are still around 2 orders of magnitude above that, mostly to these kinds of systematics that we are dealing with. Having said that, we have already begun the phase 2 of the experiment. So here we have replaced the feeds which were operating between 100 and 200 megahertz to another Vivaldi feeds, which are 50 to 250 megahertz. So we already have around 500 good nights with around 200 antennas, and we are now coming up with a new set of upper limits for a very wide range of frequencies. So this is a preliminary plot coming very soon, where we have now upper limits on the power spectra all the way to redshifts of 24. So this is going to be very exciting because we have never operated in this regime. And this itself can help us in a lot of theoretical constraints. So please keep a watch on this. So now let's change gears and come to the mean component, which is the global signal. So as I said earlier, for power spectrum, you do need interferometric measurements because you are measuring different modes on the sky. That's not the case for the mean signal. So the mean signal, if you have a single antenna, which is very well calibrated, can give you a measurement of the global signal. So this is similar to your CMB, where your spectrum is like a black body, right? So that is the monopole component. And then you have fluctuations or the anisotropies, which are captured in your power spectrum. So a very similar kind of an argument here. So this is similar to, for example, the black body spectrum, a single absolute measurement. Again, there are lots of experiments on the horizon. It is certainly not an exhaustive list. After these experiments, we also have experiments like REACH and MIST, which are already operating. But I would be mostly talking about the SARAS experiment, which is here developed at RRI. And this is already in a state where it's undergoing a lot of upgrades and also taking a lot of measurements. So this was initiated in the late 2000s by Professor Ravi Subramaniam here at RRI, but it has operated over more than 20 years now. And over that time scale, it has also evolved substantially from its first design. So the left side plot is what was the first version of SARAS, which is the dipole antenna. It was deployed in Gauri Bidnoor field station. But with time, we also learned a lot of lessons on how to calibrate our experiments better, how to make changes so that our systematics are easier to model. And that has led to the current design, which is SARAS 3, that actually floats on lakes rather than operating on land. And that actually makes it very unique when you make it, when you compare it with other experiments that are going around. Also, SARAS is not a permanent installation, unlike other experiments. It's more of what a colleague of mine calls a nomadic experiment, where you take it out, observe for a month or so, collect data, analyze it, The analysis of the data also gives you insight on how to make your system better. So therefore you upgrade the system and continue this process. So it has gone to all different places. And then it has also, every deployment has come up with a unique design of the system, an improvement over the previous one. It's not just me, of course, it's an experimental effort requiring help from a lot of people. So before I talk about Saras, a big shout out to all our team members, including a lot of moving population of visiting students and also very active support that we get from observatories and our field stations. So as I said, what is more important for these experiments is the frequency response. So a recap is your foreground is spectrally smooth, your signal is not. And if your experiment could preserve this, you could in some way filter out the smooth components and recover the signal of interest. But if there is any feature in your experiment that can introduce a feature like what your signal has, it gets almost impossible to separate the two things. So what we really want is the instrument should not have any deviations from spectral smoothness at very high levels of precision. And this is very challenging. Okay. So we have tried to keep the system as simple as possible to avoid any kind of non-smooth features. We have an antenna, which is a monopole antenna, probably one of the simplest designs, what we call as disc cone, which floats on water. The utility of using water I'll come to later, but essentially it avoids a lot of unwanted systematics. Just below the antenna, you have the front-end receiver. The zoomed-in picture is shown here, but this is nothing but around 10 to 15 centimeters in length, the actual front-end receiver part. And then over optical fibers, you have the rest of the system on the back end, where you digitize the signal and then you do a cross correlation to get the spectrum of the sky, which is the brightness temperature as a function of frequencies. So coming a little bit more on the technical side, this is what the schematic of our experiment. So as I said, we have a disc cone antenna, and just below is our front-end switch, a front-end receiver. This front-end receiver essentially toggles between antenna and a standard calibrator. So unlike interferometers, where you were observing a given region on the sky, making maps, subtracting it, and that was your way to also calibrate your experiment, here we can't rely on the sky. We actually use an inbuilt calibrator where we know the response of the calibrator to a very high accuracy. And on a particular cadence, we keep on injecting that in our system to derive the calibration. And this is what we would call the backend, which is on the other side of the optical fiber, where we have the phase switching to cancel some additional systematics. And finally, the digital cross correlation, which is housed in an electromagnetically shielded chamber so that any radiation from here doesn't get picked up by the antenna. And these two systems, the front end and the back end systems, are perfectly isolated. Therefore, any contribution from here should not travel towards the front end and add to the data, right? So that is how what the system looks like. As I said, it's an ongoing activity. So the second version of Saras, which observed in 100 to 200 megahertz, already ruled out a few models which were theoretically plausible. And you can see a very distinct feature of all these signals. The color ones are the ones that are ruled out. And they correspond to very deep troughs and also very rapidly going to zero. So this in astrophysical parameter space is a hallmark of very poor X-ray efficiency as well as very high ionization rate. This was carried forward in more detail by Bevins and others at Cambridge, where we also looked at not just the standard signals, but also a lot of non-standard signals. And by that, what I mean is there might be cases where you have a lot of excess radio background. So your TR term in that equation no longer only comprises CMB, but also radiation from the very first galaxies. And with different models of systematics, noise, and signals, we were able to place very good constraints on the luminosities of these first sources. So the blue solid curve here is what you would expect when you had the full parameter space available to you. And the red ones, especially the darker ones, are the ones which are right now allowed by Saras 2 observations. So using this, of course, you can also constrain the astrophysical parameters or the combination of them. Then came another very big study and detection correspondingly in our field in 2018, which is another experiment called EDGES, which is operating in Western Australia. It claimed a detection which was the black solid line. And you can already see why it was so anomalous compared to the standard signals that we are used to looking at. It has huge depth. This amplitude is unexpected. And the shape of the signal is also very difficult to explain unless you evoke some very non-standard models. So there is a lot of nuance here in terms of how you arrive at this conclusion. So we also tried to show the same data set can be interpreted differently. But the best way to answer and to verify any of this is if you have a measurement from your own experiment. And that's exactly what we did. So this was done in Karnataka here, where we had roughly 15 hours of good data from doing observations in some remote areas. And this is what we got. So this is the foreground dominated measurement of the sky after you have done your best to correct for every possible systematics in your data. And this plot shows you the residuals after you have subtracted any unmodeled systematics and the foregrounds. So clearly, when you test for the kind of signal which was detected by the other experiment, you kind of don't find that in these residuals. That is where you expect them to find. You can also try to jointly model them and try to see whether your data is consistent with the presence of the signal or the absence. It's a very binary question. And the idea was when we jointly modeled, we found that our data is more consistent with the absence of the signal. Or in other words, our scale factor or the amplitude of the signal was consistent with being 0. So this was a refutal of a claim that was made by the other experiment. And therefore, the signal which was detected by edges has been ruled out, but it also means that we are back to square one, right? So we started from a non-detection, went to a detection, which was very anomalous, but then we realized, given that it was not observed by other experiment, that it was probably a calibration artifact, and therefore we need more work in order to address our systematics. But at the same time, that's also a conclusion that we don't have a detection. All the signals that you saw, which have not been ruled out, are very much possible. But we have taken this work even forward and said, okay, fine, if that signal particularly is not there in the data, what can we say more about the standard signals, right? So as you see, this is a whole forest of signals here. So can we say something about it? And that has worked nicely, where we have been, with using the same data, we have been able to place constraints on things like X-ray and radioluminosities of these very first sources. But just using Saras data, as you can see, it's not an individual constraint, but a combination. For example, you can constrain some parameter space which has some ranges of luminosities in radio along with certain staff efficiency. But that's where the idea came that what if we start combining different observations? So why do we have to restrict only with the global signal or only with the power spectrum? What happens when you start combining them together? Because eventually they are measuring the same 21 centimeter brightness field, right? So with individual Saras 2 and Saras 3, we have been able to rule out a bunch of these models, which are what is shown in green and red, while the blue is the full parameter space. But now we have started to put the measurements together. So we have some kind of upper limits from Hera and some kind of upper limits from Saras, one looking at the global signal, one looking at the power spectrum. What if we simply combine their likelihoods, right? Which was a very interesting exercise. It's very computationally expensive because you are sampling over such a wide parameter space of astrophysics. Nothing is really constrained there. But eventually you can do that. And that leads to much better constraints on all these astrophysical parameters. So the kind of things we are looking at is star formation efficiency, the luminosities in both X-ray and radio bands, and also what is the minimum mass to form these halos. So our best constraints actually come on the luminosities of these sources in X-rays and radio, right? And this actually is more of a technique where you can show how much you gain by combining different things. So if you have a prior of, okay, all of these are possibilities of what the nature of the first stars and galaxies are, how much of it are you able to rule out? So what volume of your prior is still consistent with the data once you put your data in. So if you can't constrain anything, it will be 100%. So your prior and posterior are same. But then if your data has constraining power, posterior volume will be much lesser. So as you can see, the moment you start combining different measurements, not just Saras 3, Saras 2, but Saras 3, Saras 2, Hera, you start getting more and more constraints on your posterior. So you're able to rule out a lot of priors, which are possible from theory side, but definitely your data does not allow for that. And this is where the synergy between different experiments come in. So this is one of the tightest constraints that we have found on the luminosities of these sources, just from non-detections from different experiments. I would want to emphasize that, which is if your limits are very sensitive, you can do a lot by combining these, even if they are non-detections. Okay. And then why stop only at the power spectrum and the global signal? You can go further. So here we also started looking at combining with diffuse X-ray background as well as the arcade measurements, which had a claim that there is excess radio background. And of course, as you expect, the moment you combine these additional observations, your posteriors on the properties of these sources further get tighter and enhanced. So your significance on your astrophysical parameter space is much higher now. Okay. So I have only a few minutes left. So I'll quickly go through the second part, smaller part rather, on what are we doing after the last observations. So we have taken a three-pronged approach. We have to continue making our receiver better because the calibration systematics are always present and there is an ongoing effort on how to minimize them. Antenna systematics are way more challenging because that is something you don't calibrate. And I'll try to qualify this statement by going back to my schematic of the system. All your calibration is happening after the antenna, right? So any variation from after the antenna can in principle be taken into account, at least the multiplicative ones, but that's not the case for the antenna response itself, right? So in some way, antenna systematics have to be dealt separately, and that's why I have put it as a separate category here. And finally, a lot of these locations where we had observed historically are unfortunately no longer radio quiet, which is also a big concern that the sites or finding sites which are radio quiet that don't have a lot of terrestrial interference, that number is continuously reducing. So all of these things have been taken into account. The first thing, as I said, is receiver calibration. We have made a lot of changes in the receiver so that our system is more stable and smoother with frequency, which basically says that when you model your measured data with this kind of an instrument, you will probably have more confidence over your detection or the limit. Antenna systematics, it floats on water, and I always get a lot of questions on how stable your antenna is, what about the tilt of your antenna. All of this we have taken into account thanks to a lot of very nice simulations done by Kavita and Vishaka here, where we have taken all of these different realistic variations of our antenna properties, both their field of view as well as their multiplicative response, and then done a forward model, which was led by my PhD student Yash. And using this, you can basically now say, okay, certain kinds of antenna systematics are allowed because they don't compromise my detection. And the way to do that is you inject a known signal in your data and try to see if you can recover it under that particular perturbation of your instrument. So these are different perturbations that you have put. And for each perturbation, it's not a single signal that we are looking for. So we have taken different kinds of signals and tried to see how much of a bias we incur. So in some way that it constrains on what kind of antenna systematics are allowed and what are not allowed. A related thing is what we would call the S11. I can't again go into the details, but this is the transfer function of your antenna. And you need a very careful measured and a very accurate measure of this quantity in order to undo those effects in your data. So we have also developed a system where we have been able to measure it to the required accuracy and undo these things in the data. Last but not the least, the radio quiet locations. So the site where we had our observation is become radio loud thanks to a lot of terrestrial sources that have come up. So we have a small portable system which we have taken it literally all over the world at this point and characterize different kinds of location. So just to orient you, this is what we call as dynamic waterfall. You have time on the vertical axis and frequency on the horizontal. The bright spots are very high powers. So for example, you would expect FM, so that is around 87 to 108 megahertz. But then you have some satellites, you have some very broadband emissions at low frequencies, and so on and so forth. So this was observed at Gauribidnur, which is a radio observatory close by, where you expect these kind of sources to be there. But then you can go slightly far from the civilization, where you see, for example, this is in Andaman Islands, very little interference. So except for a satellite here, you hardly see any other sources in our frequency range of interest. So that is a very good site to be observing at. Similarly, we have also carried out measurements in Ladakh, where we find a similar level of radio quietness, but the logistics and the access is fairly difficult here. Finally, in 2024, one of our team members, Girish, led an expedition for Arctics. So this is in a Svalbard island where we had proposed to carry out an RFI survey. So what we find is the frequency range of 100 and 200 megahertz actually is very conducive to the kind of analysis that we would want to do. And this is nicely capturing the section of the signal which is dominated by epoch of reionization. So there is a reduction in the neutral content of the universe. So we have already proposed to deploy this system here in the Arctics, operating in 100 to 200 megahertz of frequency range. And you can do a lot of nice comparisons, which we have done on how to characterize these different locations, because there are lots of variables here. For example, what kind of occupancy your interference has, what kind of terrain it has, and so on, and what kind of accessible foregrounds. So you can put them all together and look at how complicated or how straightforward and easy a site is for your observations. So that's all we have been doing on the Saras front. A very quick detour, maybe a minute or so, not more than that, is we also have been observing, right? So along with carrying out these RFI survey, we have also observed in Andaman Islands here and in Ladakh. One is actually on land, one is on water. And you can starkly see the difference, right? So in one of the sites, you have a lot of interference here, but there are some regions which are quieter. So you could, in principle, use them for your analysis. This is from the water-based deployment in Andaman, where things are much better off and you have a good fraction of the data which is not contaminated. And your instrument response also changes. So you have, for example, your antenna transfer function in blue line when it is placed in water. And the orange line is what is the antenna response when you have it on land. But in principle, you could use these measurements and correct for it in the data. So we have roughly 30 hours of data, and we are right now analyzing it and trying to get down to the sensitivity, which I'm showing you here. So the top panel is the actual brightness temperature that you measure. This is still not correcting for the antenna response. And the bottom panel is the kind of sensitivity that you have just in a single night at different frequencies. So right now we are in the process of modeling our data to reach that kind of a sensitivity. Okay. Okay, so the last section, I'll just quickly say that as you can see, we have three major issues independent of where we are. You are always affected by the terrain, whether it is water, whether it is land. The best place to be conducting that observation is actually vacuum, just from an electromagnetic point of view. You are no longer limited by the terrains. At the same time, you would want to be above ionosphere, because ionosphere, as I said, has its own set of problems. And finally, you have radio frequency interference anywhere that you go on Earth. So even if you don't have terrestrial interference, you will probably have it from satellites. So the best place really would be, first of all, in vacuum, which is space, above ionosphere. But then in Earth's orbit, you have a lot of contamination. So the best really place is if you are on the far side of the moon. Because in some way, your moon is a great block. It will shield you from all the terrestrial interference. It doesn't really have an ionosphere. And then you are in vacuum, so you're also protected from all the additional level of systematics. So this is in some way a counterpart of Saras that we are parallelly developing. And here the idea is to basically fly it eventually as a lunar mission, but the science objective remains same, which is using this kind of an experiment. You are trying to basically now look at the 21 centimeter signal from frequencies 55 megahertz to 110 megahertz, of course, including the FM band, which we don't expect to exist in the far side of the moon. So I don't think I have time to get into the details of this. So I'll quickly just go to the summary here and say that the 21 centimeter observations actually are a very good and unique window to the early universe. You can literally trace every single redshift by probing different frequencies. And the biggest challenge in these experiments is how well do you model your systematics, because the interaction of foregrounds with your instrument is not very straightforward. We have addressed a lot of these systematics over so many years now, and we are at a stage where we don't have any detection, but we do have robust limits on the non-detections. And we have been able to now use them to combine different observations and place constraints on the early universe astrophysics. And going forward, whatever one sees, whether it's an upper limit, whether it's a detection, it needs a robust cross verification from other experiments in order to have more significance on these results. So with that, I think I'm already on almost at the hour limit. So I'll stop here and take questions. Thank you.
Thanks for the nice talk. There is already one question in the chat.
Okay, the surface of the moon also has some radiation. Won't that hinder your measurements? That's a great question. And yes, the answer is it will be. Moon is largely a black body. One thing is that you are not really on the surface, but you are roughly 100 kilometers above the surface. So what you will see is one part of your antenna beam will always be looking at the moon, right? So in some way that is blocking you from looking at the foregrounds. But fortunately, because the re-radiation part of the moon is largely black body, you can assume that the part of your beam looking at the moon is roughly say 240 or 250 Kelvin. Those measurements exist. And whatever forward modeling we do take into account even the inevitable blockage by the moon. And then attributing it to a black body temperature, and then only accounting for the foregrounds which are accessible on the other side.
Okay, any more question from the audience? Anybody can unmute now and talk if they have a question. Okay, so I was asking that what is the observational evidence that the foregrounds are smooth, or like this is modeled, or this is from the data itself?
Great. It's a mix. I would refer to wonderful set of papers by my colleague Mayuri Rao and team. So there is a sky model called GMOS, and there the idea is that you do have measurements of the sky at very spot frequencies, right? So in our frequency band, which is roughly 40 megahertz to 200 megahertz, you basically have two maps: one at 150 megahertz, which is full sky, and then one at 45 megahertz, which is almost full sky. But then you can extend it to other frequencies which are not necessarily in your band. So you can go to 1420 megahertz Haslam map, which is 408 megahertz. And then you get into the W map and Planck territory after that. So you can use all of these very precise maps and have a physical model that governs this. So you can basically write down an equation where you have synchrotron radiation, you have Rem-Stolung, you have black body component, and now for every region of the sky, you take these measurements from different maps and model it. So that's what my colleague had done. And once you put that physics into the model, you will realize that the moment you start averaging these over the field of view of your experiment, you can, independent of where you are looking, you should be able to model them as smooth functions all the way to millikelvin accuracies. But of course, it critically depends on how accurate your models are or your sky measurements are. So in some way, you would want to in future conduct more and more such measurements, probably to better accuracies, and continue to refine this.
Thank you. And another question was, what is spin temperature and how is it getting coupled to different epochs, to different
Perfect.
temperatures? What is the physics
Yes.
behind it?
Yeah. So just to go back to that. Yeah. So the spin temperature is actually a very fascinating concept. It's not a temperature to start off with, right? It's basically you have a hydrogen atom which can have two spin states where your electron and proton either have the same spin or opposite spins. And it's the ratio of these two populations, which we actually refer to as spin temperatures. So yeah, it's not a temperature, but it's a ratio of the populations. Now you can imagine there are processes that can change this ratio. So if suppose you have an electron and a proton with the kind of spins which is shown on the slide here. Suppose there is a collision or there is an excitation. What it can do is the electron spin can flip. And suddenly your population of the singlet and triplet states, which are opposite spins and parallel spins, can change. And they are governed by three distinct temperatures. So what can really cause the spin flip? The one thing is background temperature, the CMB basically, or if there is other contribution to it. The other is Lyman alpha photons, because if you have Lyman alpha photons, they can excite the electrons. And then when they come back, they have equal probability of coming in the same spin or the opposite spin. And then you have the actual gas temperature, because that governs the collisions between electrons. So all of these have the capability to change the spin, the ratio of the two populations. So in some way, even if your spin temperature is not a temperature, it couples to one of these at different times in the cosmic history. So initially it is coupled to radiation, because radiation and matter are also coupled. At early stages, it is tightly coupled to radiation because your collisions are very high. But as your density reduces, your collision becomes ineffective. But then at some point, what happens is there is Lyman alpha, which again couples it back to the kinetic temperature or the gas temperature. So essentially, over this entire cosmic history, the kind of signal that I showed you, the spin temperature is coupled to different temperatures at all these different redshifts. But essentially, from here, when we expect the first galaxies to form, because they emit these Lyman alpha photons, which can couple the spin temperature to gas temperature, from here we expect the spin temperature to be a proxy for gas. But before this, it can couple to different quantities.
Okay, thanks for the answer. And there is another question in the chat.
Is there any possibility of making polarization observations? Would it be helpful in the, yeah, great. Yeah, polarization is one thing that I could not touch upon. And polarization matters a lot because similar to what Arithro asked, which is when we talk about the smoothness of foregrounds, we are essentially looking at mostly the total intensity map. But Saras, or for that matter, any of these experiments, independent of their architecture, they're mostly sensitive to one single polarization. So Saras also observes only one polarization, which is governed by the design of the antenna. So here, in some way, it would always help you to have the other polarization measurement. And in some way, this is probably more important for power spectrum measurements. For global experiments, we have not yet hit the limitation where we think that there are these polarized structures which are contributing to some kind of systematics. And the potential reason for that is our field of view is really big. So we are talking about 40 degrees to 50 degrees field of view. And most of our radio sky, when you convolve over such a big thing, the single polarization measurement will expectedly be spectrally smooth. But having said that, if you want a more robust modeling of your actual sky, instead of having to rely only on the smoothness property of foregrounds, you are better off measuring both polarizations. And this is an approach that has been taken by experiments like EDGES and REACH, where they too attempt to make multiple measurements from different polarizations.
So thanks for the answer. There is
Yeah.
another question.
Yeah, there is another question. So this is, I probably missed it with respect to non-detection and that aiding in constraining parameters. How do you deal with possible parameter degeneracies? Yeah, I mean, right now we really can't do much. So I'll give an example, which is this. So first of all, you're absolutely correct. There are lots of degeneracies in our model space. So one example is when we modeled Ceres 3, I probably had. So for example, these kinds of very narrow ellipses are telltale signatures. And to some extent, they are factored in your posterior because you are marginalizing over it. It will end up, of course, increasing your error bars. But at the end of the day, you kind of account for them when you quote your results, and therefore that is factored in the significance that you present. But the way to break it is not possible with just a single experiment because they are intrinsic to the experiment. The way to break that is having different observables which are sensitive to different parts of your parameter space. So I did not have enough time to be discussing this plot, but now since you brought it up, for example, your radio measurements, particularly the 21 centimeter measurements, they are very sensitive to the cold gas scenario because when the IgM gas is very cold, it will lead to higher amplitude of the signal. So in some way, if you don't find a very high amplitude signal, which is what we have been doing, you can place a constraint that your luminosity of X-ray should be higher than a certain limit, right? So in some way, you are placing a lower limit on your luminosity. And that's about it. You can't do better than that with 21 centimeter observation. It's a limitation of your model. But now when you put in some other thing, for example, Chandra has a measurement of unresolved X-ray background. Now suddenly, if you have very high luminosity X-ray sources, they will very rapidly violate these upper limits that are placed by Chandra on the unresolved X-ray background. So with just 21 centimeter experiments like Saras or Hera, you see these green lines. So your probability increases, but you are able to rule out the lower side of the luminosity. But now with X-ray background, which is pink, it's the other way around. You are not sensitive to low values because they are well within the Chandra upper limits. But the moment you have very energetic X-ray sources with very high luminosities, it will defavor them, right? So by combining these, you can break these kinds of degeneracy. And now you have a posterior, which is two-tailed. So you have a lower as well as an upper limit. So going forward, combining these kinds of observation is really the best way to go.
Okay, any other questions? Okay, then Saurabh, thanks for the nice talk.
Thanks a lot for inviting me for the talk.
Thank you.
Thanks all.
Okay, then.
Bye.